In chemistry, post-transition metals are the metallic elements in the periodic table located between the transition metals and the metalloids. Usually included in this category are gallium, indium and thallium, tin and lead, and bismuth. Which elements are counted as post-transition metals depends, in periodic table terms, on where the transition metals are taken to end and where the metalloids and non-metals are taken to start. Physically, post-transition metals are soft, have poor mechanical strength, and melting points lower than those of the transition metals. Most also have boiling points lower than those of the transition metals. Being close to the metal-non-metal border, their crystalline structures tend to show covalent or directional bonding effects, having generally greater complexity or fewer nearest neighbors than other metallic elements. Chemically, they are characterized, to varying degrees, by covalent bonding tendencies, acid-base amphoterism and the formation of anionic species such as aluminates, stanates, and bismuthates. They can also form zintal phases. The expression post-transition metals is used here as there is no IUPAC-approved collective name for these metals. Occasionally, some or all of them have instead been referred to as B-subgroup metals, other metals, or P-block metals, and by at least 11 other alternative labels. All these labels are surveyed later in this article. Applicable elements, usually included in this category, are the group 13 to 15 metals, gallium, indium and thallium, tin and lead, and bismuth. Other elements sometimes included are copper, silver and gold, zinc, cadmium and mercury, and aluminium, germanium, arsenic and antimony. Astatine, which is usually classified as a non-metal or a metalloid, has been predicted to have a metallic crystalline structure. If so, it would be a post-transition metal. Elements 113 to 117 may be post-transition metals. Insufficient quantities of them have been synthesized to allow investigation of their actual physical and chemical properties. Which elements start to be counted as post-transition metals depends, in periodic table terms, on where the transition metals are taken to end. In the 1950s, most inorganic chemistry textbooks defined transition elements as finishing at group 10, therefore excluding group 11, and group 12. A survey of chemistry books in 2003 showed that the transition metals ended at either group 11 or group 12 with roughly equal frequency. Where the post-transition metals end depends on where the metalloids or non-metals start. Boron, silicon, germanium, arsenic, antimony and tellurium are commonly recognized as metalloids. Other authors treat some or all of these elements as non-metals. Rationale: the diminished metallic nature of the post-transition metals is largely attributable to the increase in nuclear charge going across the periodic table, from left to right. The increase in nuclear charge is partially offset by an increasing number of electrons, but as these are spatially distributed, each extra electron does not fully screen each successive increase in nuclear charge, and the latter therefore dominates. With some irregularities, atomic radii contract, ionization energies increase, fewer electrons become available for metallic bonding, and ions smaller and more polarizing and more prone to covalency. Quote, this phenomenon is more evident in period 4 to 6 post-transition metals, due to inefficient screening of the nuclear charges by the D10 and F14 electron configurations. The screening power of electrons decreases in the sequence S and GT, P and GT, D and GT, F. The reductions in atomic size due to the interjection of the D and F blocks are referred to as, respectively, the candide or D-block contraction, and the lanthanide contraction. Relativistic effects also increase the binding energy, and hence ionization energy, of the electrons in the 6s shell in gold and mercury, and the 6p shell in subsequent elements of period 6. Nomenclature. Origin. The origin of the term post-transition metal is unclear. An early usage is recorded by Deming in 1940 in his well-known book Fundamental Chemistry. He treated the transition metals as finishing at group 10. He referred to the ensuing elements in periods 4 to 6 of the periodic table, in view of their underlying D10 electronic configurations, as post-transition metals. Descriptive chemistry. This section outlines relevant physical and chemical properties of the elements typically as sometimes classified as post-transition metals. For complete profiles, including history, production, specific uses, and biological roles and precautions, see the main article for each element. Abbreviations: mH, Mohs hardness, BCN, bulk coordination number. Group 11. The group 11 metals are typically categorized as transition metals given they can form ions with incomplete D shells. Physically, they have the relatively low melting points and high electronegativity values associated with post-transition metals. The filled D subshell and free s electron of Cu, Ag, and O contribute to the high electrical and thermal conductivity. Transition metals to the left of group 11 experience interactions between s electrons and the partially filled D subshell, the lower electron. Mobility. Chemically, the group 11 metals in the +1 valence states show similarities to other post-transition metals. They are occasionally classified as such. Copper is a soft metal with low mechanical strength. It has a close-packed face-centered cubic structure. Copper behaves like a transition metal in its preferred oxidation state of +2. Stable compounds in which copper is in its less preferred oxidation state of +1 have significant covalent character. The oxide is amphoteric, with predominating basic properties. It can be fused with alkali oxides to give anionic oxycuprates. Copper forms zintal phases such as Li7 copperate silicide and M3 copper 4 antimonide. Silver is a soft metal with low mechanical strength. It has a close-packed face-centered cubic structure. The chemistry of silver is dominated by its +1 valence state, in which it shows generally similar physical and chemical properties to compounds of thallium, a main group metal, in the same oxidation state. It tends to bond covalently in most of its compounds. The oxide is amphoteric, with basic properties predominating. Silver forms a series of oxoargentates. It is a constituent of zintal phases such as Li2AgM and Yb3Ag2. Gold is a soft metal that is easily deformed. It has a close-packed face-centered cubic structure. The chemistry of gold is dominated by its +3 valence state. All such compounds of gold feature covalent bonding, as do its stable +1 compounds. Gold oxide is amphoteric, with acid properties predominating. It forms anionic hydroxoates M where M equals Na K 1/2 bar Tl and aurates such as NaO2. Gold is a constituent of zintal phases such as M2Orb, Li2AuM and California 504. Group 12. On the Group 12 transition metals, Smith observed that textbook writers have always found difficulty in dealing with these elements. There is an abrupt and significant reduction in physical metallic character from Group 11 to Group 12. The chemistry is that of main group elements. A 2003 survey of chemistry books showed that they were treated as either transition metals or main group elements on about a 50/50 basis. The IUPAC Red Book notes that although the group 3-12 elements are commonly referred to as the transition elements, the group 12 elements are not always included. The group 12 elements do not satisfy the IUPAC Gold Book definition of a transition metal. Zinc is a soft metal with poor mechanical properties. It has a crystalline structure that is slightly distorted from the ideal. Many zinc compounds are markedly covalent in character. The oxides of zinc in its preferred oxidation state of +2, namely zinc oxide and zinc 2, are amphoteric. It forms anionic zincates in strongly basic solutions. Zinc forms zintal phases such as LiZn, NaZn13 and Bazn13. Highly purified zinc, at room temperature, is ductile. It reacts with moist air to form a thin layer of carbonate that prevents further corrosion. Cadmium is a soft, ductile metal that undergoes substantial deformation under load at room temperature. Like zinc, it has a crystalline structure that is slightly distorted from the ideal. The halides of cadmium, with the exception of the fluoride, exhibit a substantially covalent nature. The oxides of cadmium in its preferred oxidation state of +2, namely cadmium oxide and CD2, are weakly amphoteric. It forms cadmates in strongly basic solutions. Cadmium forms zintal phases such as LiCd, RbCd13 and CsCd13. When heated in air to a few hundred degrees, cadmium represents a toxicity hazard due to the release of cadmium vapor. When heated to its boiling point in air, the cadmium vapor oxidizes, with a reddish-yellow flame, dispersing as an aerosol of potentially lethal cadmium oxide particles. Cadmium is otherwise stable in air and in water at ambient conditions, protected by a layer of cadmium oxide. Mercury is a liquid at room temperature. It has the weakest metallic bonding of all, as indicated by its bonding energy and melting point, which together are the lowest of all the metallic elements. Solid mercury has a distorted crystalline structure with mixed metallic covalent bonding and a BCN of 6. All of the metals, but especially mercury, tend to form covalent rather than ionic compounds. The oxide of mercury in its preferred oxidation state is weakly amphoteric, as is the congener sulfide mercury 2 sulfide. It forms anionic thiomercurates in strongly basic solutions. It forms or is a part of zintal phases such as NaHg and K8 and 10Hg. Mercury is a relatively inert metal, showing little oxide formation at room temperature. Group 13 aluminium sometimes is or is not counted as a post-transition metal. It has a well-shielded noble gas core rather than the less well-shielded 3D10, 4D10 or 4F145D10 core of the post-transition metals. The small radius of the aluminium ion combined with its high charge make it a strongly polarizing species, prone to covalency. Aluminium in pure form is a soft metal with low mechanical strength. It has a close-packed structure showing some evidence of partially directional bonding. It has a low melting point and a high thermal conductivity. Its strength is halved at 200 degrees Celsius, and for many of its alloys is minimal at 300 degrees Celsius. The latter three properties of aluminium limit its use to situations where fire protection is not required, or necessitate the provision of increased fire protection. It bonds covalently in most of its compounds, has an amphoteric oxide, and can form anionic aluminates. Aluminium forms zintal phases such as Lil, California 3 aluminium antimonide, and SrAl2. A thin protective layer of oxide confers a reasonable degree of corrosion resistance. It is susceptible to attack in low pH and high pH conditions, a phenomenon that is generally more pronounced in the case of commercial purity aluminium and aluminium alloys. Given many of these properties and its proximity to the dividing line between metals and nonmetals, aluminium is occasionally classified as a metalloid. Despite its shortcomings, it has a good strength-to-weight ratio and excellent ductility. Its mechanical strength can be improved considerably with the use of alloying additives. Its very high thermal conductivity can be put to good use in heat sinks and heat exchangers, and it has a high electrical conductivity. At lower temperatures, aluminium increases its deformation strength whilst maintaining ductility. Chemically, bulk aluminium is a strongly electropositive metal with a high negative electrode potential. Gallium is a soft, brittle metal that melts at only a few degrees above room temperature. It has an unusual crystalline structure featuring mixed metallic covalent bonding and low symmetry. It bonds covalently in most of its compounds, has an amphoteric oxide, and can form anionic galates. Gallium forms zintal phases such as Li2Ga7, A3Ga13 and YbGa2. It is slowly oxidized in moist air at ambient conditions. A protective film of oxide prevents further corrosion. Indium is a soft, highly ductile metal with a low tensile strength. It has a partially distorted crystalline structure associated with incompletely ionized atoms. The tendency of indium to form covalent compounds is one of the more important properties influencing its electrochemical behavior. The oxides of indium in its preferred oxidation state of +3, namely in 2O3 and in 3, are weakly amphoteric. It forms anionic indates in strongly basic solutions. Indium forms zintal phases such as LiIn, Na2in and Rb2in3. Indium does not oxidize in air at ambient conditions. Thallium is a soft, reactive metal, so much so that it has no structural uses. It has a close-packed crystalline structure but an abnormally large interatomic distance that has been attributed to partial ionization of the thallium atoms. Although compounds in the +1 oxidation state of the more numerous, thallium has an appreciable chemistry in the +3 oxidation state, as seen in its chalcogenides and trihalides. It is the only one of the group 13 elements to react with air at room temperature, slowly forming the amphoteric oxide Tl2O3. It forms anionic phthalates such as TL3TLO3, Na3 teraliters 6, NaTlO2, and KTlO2, and is present as the Tl- phthalide anion in the compound CSTL. Thallium forms zintal phases, such as Na2 teraliters, Na2K21 teraliters 19, CSTL and Senior 5 teraliters 3H. Group 14 germanium is a hard, very brittle semi-metallic element. It was originally thought to be a poorly conducting metal but has the electronic band structure of a semiconductor. Germanium is usually considered to be a metalloid rather than a metal. Like carbon and silicon, it has a covalent tetrahedral crystalline structure. Compounds in its preferred oxidation state of +4 are covalent. Germanium forms an amphoteric oxide, germanium peroxide, and anionic germanates, such as Mg2 germanium oxide. It forms zintal phases such as LiGe, K8Ge44 and La4Ge3. Tin is a soft, exceptionally weak metal. A 1 cm thick rod will bend easily under mild finger pressure. It has an irregularly coordinated crystalline structure associated with incompletely ionized atoms. All of the group 14 elements form compounds in which they are in the +4, predominantly covalent, oxidation state. Even in the +2 oxidation state, tin generally forms covalent bonds. The oxides of tin in its preferred oxidation state of +2, namely tin2 oxide and SN2, are amphoteric. It forms stannides in strongly basic solutions. Below 13 degrees Celsius, tin changes its structure and becomes gray tin, which has the same structure as diamond, silicon and germanium. This transformation causes ordinary tin to crumble and disintegrate since, as well as being brittle, gray tin occupies more volume due to having a less efficient crystalline packing structure. Tin forms zintal phases such as Na4SN, BASN, K8SN25 and California 31SN20. It has good corrosion resistance in air on account of forming a thin protective oxide layer. Pure tin has no structural uses. It is used in lead-free solders, and as a hardening agent in alloys of other metals, such as copper, lead, titanium and zinc. Lead is a soft metal which, in many cases, is unable to support its own weight. It has a close-packed structure but an abnormally large interatomic distance that has been attributed to partial ionization of the lead atoms. It forms a semi-covalent dioxide lead-2 peroxide, a covalently bonded sulfide lead-2 sulfide, covalently bonded halides, and a range of covalently bonded organolet compounds such as the lead mercaptan Pb2, lead tetraacetate Pb4, and the once common anti-knock additive tetraethyl lead 4 petabits. The oxide of lead in its preferred oxidation state is amphoteric. It forms anionic plumbates in strongly basic solutions. Lead forms zintal phases such as CSPb, senior 31 petabits 20, La5 petabits 3N and YB3 petabits 20. It has reasonable to good corrosion resistance. In moist air it forms a mixed gray coating of oxide, carbonate and sulfate that hinders further oxidation. Group 15 arsenic is a moderately hard and brittle semi-metallic element. It is commonly regarded as a metalloid, or by some other authors as either a metal or a non-metal. It exhibits poor electrical conductivity which, like a metal, decreases with temperature. It has a relatively open and partially covalent crystalline structure. Arsenic forms covalent bonds with most other elements. The oxide in its preferred oxidation state is amphoteric, as is the corresponding oxoacid in aqueous solution and congener sulfide. Arsenic forms a series of anionic arsenates such as sodium arsenide and PbSO4 and zintal phases such as sodium arsenide, calcium arsenide and SRase3. Antimony is a soft and brittle semi-metallic element. It is commonly regarded as a metalloid, or by some other authors as either a metal or a non-metal. It exhibits poor electrical conductivity which, like a metal, decreases with temperature. It has a relatively open and partially covalent crystalline structure. Antimony forms covalent bonds with most other elements. The oxide in its preferred oxidation state is amphoteric. Antimony forms a series of anionic antimonites and antimonates such as NaSbO2 and AlSbO4 and zintal phases such as potassium antimonide, senior 2sb3 and barium antimonide. Bismuth is a soft metal that is too brittle for any structural use. It has an open-packed crystalline structure with bonding that is intermediate between metallic and covalent. For a metal, it has exceptionally low electrical and thermal conductivity. Most of the ordinary compounds of bismuth are covalent in nature. The oxide, bismuth oxide, is predominantly basic but will act as a weak acid in warm, very concentrated Co. It can also be fused with potassium hydroxide in air, resulting in a brown massive potassium bismuthate. The solution chemistry of bismuth is characterized by the formation of oxyanions. It forms anionic bismuthates in strongly basic solutions. Bismuth forms zintal phases such as NaB, Rb7 N4/6 and Bar11 CDH/14. Byler et al. Refer to bismuth as being the least metallic metal in its physical properties given its brittle nature, the lowest electrical conductivity of all metals. Group 16 polonium is a radioactive, soft metal with a hardness similar to lead. It has a simple cubic crystalline structure characterized by partially directional bonding, and a BCN of 6. Such a structure ordinarily results in very low ductility and fracture resistance. However, polonium has been predicted to be a ductile metal. It forms a covalent hydride. Its halides are covalent, volatile compounds, resembling those of tellurium. The oxide of polonium in its preferred oxidation state is predominantly basic, but amphoteric if dissolved in concentrated aqueous alkali, or fused with potassium hydroxide in air. The yellow polonate ion polonium-2 peroxide-3 is known in aqueous solutions of low Cl concentration and high pH. Polonides such as Na2Po, BePO, ZnPO, CdPO and HgPO feature Po2- anions. Except for HgPO, these are some of the more stable of the polonium compounds. Group 17 astatine is a radioactive element that has never been seen. A visible quantity would immediately be vaporized due to its intense radioactivity. It may be possible to prevent this with sufficient cooling. Astatine is commonly regarded as a non-metal, less commonly as a metalloid and occasionally as a metal. Unlike its lighter congener iodine, evidence for diatomic astatine is sparse and inconclusive. In 2013, on the basis of relativistic modeling, astatine was predicted to be a monatomic metal, with a face-centered cubic crystalline structure. As such, astatine could be expected to have a metallic appearance, show metallic conductivity, and have excellent ductility. Even at cryogenic temperatures, it could also be expected to show significant non-metallic character, as is normally the case for metals in or in the vicinity of the p-block. Astatine oxyanions: astatine monoxide minus, astatine monoxide -2, astatine monoxide -3 and astatine monoxide -4 are known. Oxyanion formation being a tendency of nonmetals. The hydroxide of astatine that is presumed to be amphoteric. Astatine forms covalent compounds with nonmetals, including hydrogen astatide hat and carbon tetraestate cat4. At- anions have been reported to form astatides with silver, thallium, palladium and lead. Prushinsky et al. Note that astatidines should form strong complexes with soft metal cations such as Hg2+, Pd2+, Ag+, and Tl3+. They list the astatide formed with mercury as Hgad.